Here's another application of differentials, using them to estimate error or to make sure that we restrict the error. We're using error tolerances here. So we're asked about the error that we can have in diameter to measure the volume within 3%. So what we want to first connect is the fact that we have a sphere, of course, so think this circle is three-dimensional. We need to discuss the volume of the sphere in terms of diameter. So you maybe remember volume is a cubic unit. The formula for sphere is 4/3 pi r cubed is the volume of a sphere, but we don't have radius. We're asked to do this with diameter. So we need to connect diameter and radius. Diameter is twice the radius, so we can solve for radius r is half the diameter. That gives us a new equation for volume. Volume is 4/3 pi. Radius is half the diameter. Cubed, let's clean that up. Volume is 4 pi d cubed, and the denominator 2 cubed is 8. So divided by 3 times 8, let's get rid of that. 4 and 8 make it half. So really just 1/6. 1/6 pi times d cubed is the volume. That's our formula for volume. And what we want to do with that volume, the differential bit, the percentage of error in the diameter compared to the error in the volume. We want to restrict the error on the volume. We want to find that the change in volume, positive or negative, is less than 3%, 0.03 of the actual volume. And what we found so far is a volume formula right there. But we also need to discuss the change in volume formula, the dV. So the change in volume is just the derivative of this guy. So you look over here at this black equation, d is the variable, bring down the 3, 1/6 pi times the derivative of d cubed, 3d squared times the differential change in diameter, dd, by the chain rule or by the differential formula where we have this guy as f prime and this guy as the dx, or in this case it's a dd, that's our variable. So now we have a volume formula and a change in volume formula, dv. Simplify 1/6 times 3 is half, so pi over 2 times d squared dd, the change in diameter. Okay, so let's go back over to this want formula and fill out that equation. We want the change in volume, so the absolute value of pi over 2 diameter squared times the change in diameter, to be less than 0.03 or 3% of the true volume, 4/3 pi. Oh, we fixed it. Not 4/3 pi r cubed, but this guy. Pi over 6 times the diameter cubed. Okay, so d squared always positive, pi and 2 also always positive, they bust right out of the absolute value. Pi over 2 d squared times the absolute value of the change in diameter is less than 0.03 pi over 6 times d cubed. And then this bit, to get rid of this term, which is multiplied, we want to divide by it. And you could divide by it, or you could flip it over and multiply. So you might have a thought here that this is the same thing as pi d squared over 2. And dividing by that stuff means we just flip it over on the other side, like this. The absolute value of the change in diameter is less than 0.03 pi over 6, that d cubed is in the numerator, he's like d cubed over 1, times, what happens when we flip over the purple? 2 over pi d squared. Divide by a complex fraction, same thing as multiplying by the reciprocal. Then we can clean up this guy, like the pi's go away, which is handy, and 2 and 6 make a third, and then d cubed and d squared also cancel. So now we have that the change in diameter is less than 0.03 divided by 3, 1 times d. That means that we need to measure the diameter within 1% to get a sphere volume that is within 3%.